Hello everyone, I'm Nakamura from the Graduate School of Okayama University. Now I'm going to talk about a secondary side Resonant LLC converter for reducing resonance voltage with boost mode operation using resonance including current double rectifier. Let me start from the background. In recent years, power supply system of the servers uses isolated DC-DC converter to convert high voltage to low voltage. And then, using POL, the voltage is more stably converted to a lower voltage to operate these CPU or memories. In addition, power supply system will be like this. To deal with the development of AI or 5Gs, as well as to increase the efficiency of servers, power is transmitted at high voltage to the near the motherboard and then converted to lower voltage using this DC-DC converter. Considering this situation, this DC-DC converter must fulfill these conditions that to be high efficiency and then to be small size. LC resonant converter are expected as such DC-DC converter because LC converter can achieve sort switching operation and then can be driven at high frequency. Thus, it makes small size of passive elements. However, this converter have big problem that if you try to design this converter to have high Q factors for high response, you have the problem of high resonance voltage. This is because the high Q factor means large characteristic impedance of this resonator, especially if you achieve the high step-down ratio and then try to use this converter for high power applications. High resonance voltage will be generated, so you must make this resonator big for isolation. Thus, we consider moving the resonator to the secondary side of the lower voltage bus in order to suppress the high resonance voltage. However, if you use the center tap rectifier, as in conventional LC resonant converter, a resonant capacitor is placed on the in the DC current path. Therefore, we came up with the circuit that combines a secondary side resonance and current double rectifier so that the resonator and the DC current path can be separated. However, we consider that the converter with the secondary side resonant may not have boost operation. Generally, in conventional LC resonant converter, the nominal frequency is designed to the resonance frequency of this resonator. Therefore, at the nominal frequency, it is able to obtain constant voltage independent of the load. Then, a second resonance point using this magnetized inductance of this transformer made it possible to realize boost mode operation. However, this converter has only one resonance point. Therefore, if you design the nominal frequency to the resonance frequency of this resonator, we cannot realize the boost mode operation. Thus, a circuit with a capacitor connected to create a second resonance frequency has been proposed in recently study. This capacitor In the proposed circuit, by connecting a capacitor, a boost mode operation can be achieved even if we design the nominal frequency to the resonance frequency of this resonator. In addition, this circuit has a low resonance voltage compared to the conventional LC resonant converter, and then this converter can achieve the soft switching operation. So this converter is very expected. However, there are problems with this circuit. The current double rectifier uses a coupled transformer to reduce the size of the magnetic components. In actual magnetic components, coupled transformers have leakage inductance. The leakage inductance and this capacitor to achieve the boost mode operation cause plastic resonance. This plastic resonance causes the large spike current to flow the diode, this diode. So if you try to use synchronous rectification to improve efficiency, this is a big problem. Now, I'm going to talk about the objective and approach of my study. The objective of the research is to propose a new boost mode operation realization for secondary side resonant LLC converter. This proposed circuit has following feature that to be high efficiency. That means this converter can achieve soft switching operation, and then this converter to be a very small size. That means low resonance voltage is generated, and then no spike current flow through the diode. And then our approach is to use the reactance of the coupled transformer, this transformer. In the previous study, the coupled transformer of the current double rectifier was considered to be a just transformer. In other words, we were considering it under the condition the magnetizing inductance of this coupled transformer is very large. However, if this magnetizing inductance of this coupled transformer is very small, we can consider this coupled transformer is just coupled inductor. So if the nominal frequency is designed to be the resonance frequency of this resonator, so that the output voltage is independent of the load, the boost mode operation can be achieved by using these red resonance points. I will now analyze the operation of this converter. The waveform shows the gate source voltage of the switches, switch 1 and switch 2, and then this waveform shows the transformer voltage and transformer current, and this waveform shows the transformer voltage and transformer current of secondary side, and this waveform shows the diode current and diode voltage. This is same, and this waveform shows the input voltage of rectifier and output current of this coupled transformer. In mode 1, the current flows in this path. The point of the inverter, the current flows through the plastic diode of the switches. In mode 2, current flow in the forward direction of in the inverter. In mode 3, the inverter current flows in forward direction, and in mode 4, the switches switch 2 and switch 3 is turned on. where current passes through the plastic diode. This circuit does not use capacitor in this line, so plastic resonance does not occur. In addition, this converter can achieve soft switching operation because this current flow plastic diode in the inverter. And then I analyze this circuit using the FHA. LC converter are often analyzed using FHA. It was checked boost mode operation can be realized using equivalent circuit. Based on the power consumption, the rectifier is replaced by an equivalent resistor. If the coupled transformer is considered as just transformer with the turn ratio of 2:1, the magnetizing inductance is expressed like this. The converter can be converted to such equivalent circuit using FHA. And then the parameter is expressed like this. If using this equivalent circuit, if the nominal frequency is designed to be this resonance frequency, we can output constant voltage independent of load. The dependence of voltage gain on the frequency was estimated using this equivalent circuit, where each parameter is shown as this. The magnetizing inductance LMCD of the coupled transformer is varied from 10 microfarad and 10 microhenry and 0.65 microhenry and 0.5 microhenry in the calculations. The result of the calculation is shown in this graph. This graph shows the calculation result where the magnetizing inductance of the coupled transformer is varied like this. The calculation results show that the boost mode operation can be realized by changing magnetizing inductance of coupled transformer. And then verification is carried out to check the operation under the following condition. This verification was carried out to investigate these 4 points that we can achieve boost mode operation, and then we can achieve soft switching operation, and we can achieve no large surge current in flow in this diode, and then we can achieve reduced resonance voltage compared to the conventional LC resonant converter. Please look at this result of experiment. The horizontal axis express switching frequency and vertical axis express output voltage. In this graph, the line shows the result of the FHA calculations, and plot shows the result of the verification. The verification results are shown where the load resistance is additionally changed 1.2 ohm and 0.72 ohm. The blue line shows the resonance frequency of this resonator, where the output voltage is independent of the load. This circuit can, looking at this characteristic, this circuit can achieve boost mode operation. Now look at this waveform. This waveform shows vertical horizontal axis express time and vertical axis express voltage or current. And then this waveform shows transformer voltage and transformer current of on primary side. Looking at this characteristic, the waveform shows the current relative to the voltage. So the load seen from the primary side of transformer is inductive. So we can achieve the sorting operation. And then please look at this waveform. This waveform shows horizontal axis show time and vertical axis express time current. And then this waveform shows diode current, this diode 1 and this diode 2. Looking in this waveform, the verification result shows that there are no sections where the both diodes are on at the same time, and then there are no surge currents. And last, the resonance voltage and the G's condition has been compared. The two circuits have the same Q factor and input voltage and output voltage. The horizontal axis expresses time and the vertical axis expresses voltage. This navy blue is conventional resonant converter, and this navy blue line. And this blue line shows the proposed resonant converter. Looking at this waveform, we can reduce the resonance voltage additionally. And then this is a conclusion of my study. Thank you for your attention.